Hey everybody, so today we're going to talk about apothems, sometimes pronounced apothems. Ugh, so gross. So we're just going to call them apothems, and you'll see soon that apothems are a really important part of the polygons that we've been talking about over the last couple weeks. So the first thing I want you to do is I want you to pause the video, and I want you to try to find the area of this regular hexagon. Go. All right, we're back. So I bet you started to think about, well, how can I break this hexagon into shapes that I know and I understand? So maybe you tried to break it into little triangles, maybe like this or like this, and then you were left with this guy. You could maybe break these into triangles. So that's all legit. That could happen. I once had a student make this into a larger triangle, which is kind of cool, and then he subtracted. Both of these are totally valid efforts and I think ultimately would work, but we're going to talk about a more efficient way. And maybe you already did this. So what if I broke my regular hexagon into these triangles? So these are 6 triangles in my 6-sided figure. And if you know, remember that a regular polygon means that all sides and all angles are congruent to each other. And because this is a regular figure, the diagonals are also going to be congruent and they bisect each other. So this is congruent to this. So I've got a nice little isosceles triangle down at the bottom. But also what's important is if I went all the way around here, I'd have 360 degrees. So 360 degrees divided by 6 is 60. So that means that if I'm looking at this triangle, that vertex angle is going to be 60 degrees. And I know that this is isosceles, so that means my bottom angles are going to be 60 because I know if sides then angles. So more than just isosceles, this is an equilateral triangle. So I now know that all my side lengths are going to be 4. So if we are looking at this triangle now, if we can figure out the area of this triangle, I know that all 6 of these triangles are the same. So let's do that first. So we're going to find the area of an equilateral triangle with side length of 4. So here's our equilateral triangle. I know that all of these guys are 4 in length. So first thing, what do you think we need to do here? I know that the area of a triangle is 1/2 base times height. Well, I've got my base, that's 4, but I don't have my height. So the height is the one thing I'm looking for here. So let's drop a tude. Ah, boom. So I'm going to drop my tude, and you know that in an isosceles or an equilateral triangle, that altitude bisects this side. But I've got a nice little 30, 60, 90 triangle here because it also bisects this angle. So I've got a 30, 60, 90 triangle, x, 2x, x root 3. So my height is going to be 2 root 3. So my height here is going to be 2 root 3. So the area of this triangle is going to be 1/2 times 4 times 2 root 3. If you're not sure how I got that, pause, rewind, and go back to it. This is really important. So that's the area of that triangle. Great. Woo! So now we're back at the original problem. So we were asked to find the area of the whole hexagon. So if I know that the area of this guy, so this little small triangle is this, the 1/2 4 times 2 root 3. So I'm just going to mix this around for a second. So instead of 1/2 base times height, I'm going to do 1/2 height times base. And there's a reason for that in a second. So we knew that our height here was 2 root 3. And we knew that our base was 4. So the area of my whole triangle is going to be 1/2 2 root 3 times 4. But if I want to find the area of the entire hexagon, I need to take the area of this triangle and I need to multiply it by the 6 triangles that I have. So like the number of sides that I have, right? Or the number of triangles that I have. So again, my height is 2 root 3. my base is 4, and then the number of sides I have is 6. I am going to turn on dual page display just so we can look at these together. So if I wanted to talk about this sort of in a general form, we have just found something really, really important. This height right here, this is our apothem. So the apothem is defined as the line segment that is perpendicular to one of the sides of a regular polygon. So from the center of that polygon to the other side, that line segment that is perpendicular from the center to the opposite side, that's what we call the apothem. And if you see on the left-hand side of your screen, that apothem is the height of your equilateral triangle. So they are the same thing. But the apothem comes into play here, and it's really, really helpful when you're doing these kinds of problems. So the apothem, if we are trying to find the area of a regular hexagon with side length 6, so let's do this here. I'm going to turn this off. So view, dual page display off. So now we're going to try and find the area of a regular hexagon, but now the side length is 6. So let's think about making our little triangle again. My base is 6, and we've got to find this height, or my apothem. So we want to find the area of the whole triangle. So remember, area is 1/2, but instead of base times height, I'm going to do height times base. So my base is 6, and we've got to figure out our height. So remember, in a 30, 60, 90 triangle, this would be 3, and then 6, and then 3 root 3. So my height, or my apothem, is 3 root 3. So my area here is going to be 1/2 times 3 root 3 times 6. But then remember, we then have to multiply it by the number of sides that we have. So multiply this by the number of sides. So times 6 again. Cool. Sorry for my delay in my pen. All right. So you're probably wondering, like, this is not a shortcut. I don't understand where this is coming from. This is really important. So the way that we figure out what the area of a regular polygon, it can be any regular polygon, a hexagon, a pentagon, whatever. So the area is 1/2 the apothem times the perimeter. And you're probably wondering where I got this. So let's go back to that previous slide. So if you look here, we said that my area was 1/2 height times base instead of base times height, but this purple thing was this triangle, right? The area of this whole triangle was 1/2 height times base. Then we multiplied that triangle, the area of that triangle, by the number of sides that we have. So look what's kind of cool here. This right here is also our apothem, right? And then if you look at this piece, 6, which is the base, times the number of sides that you have, this is your perimeter. Isn't that kind of cool? So as opposed to being like, okay, I'm going to drop the 2, and then I'm going to find this, and then I'm going to multiply it. Instead, you can just do 1/2 the apothem times the perimeter. So make sure that you have this written down. All right. Woo, there we go. So make sure that you have this written down. So 1/2 the apothem times the perimeter. That is what formula is going to help us. So let's take a peek at this. This is super straightforward. So I've got a regular pentagon, and it's got an apothem of 6.9 centimeters and a side length of 10 centimeters. So remember, the area is 1/2 the apothem times the perimeter. So I already know I've got my 1/2 here. I already know my apothem, snooze, is 6.9 centimeters. And then I've got to find my perimeter. Do not say it's 10. One side length is 10. So 10 times 5 is 50. And then you would actually do it out, right? You're not just going to leave it like that, but I'm just sort of showing you where these are coming from. So this is a really straightforward one, right? And you didn't have to like draw it out. You didn't have to think about it. You just threw it into the formula and you're done. All right. Now, I just want to remind you of the difference between circumscribed and inscribed. So on the left-hand side, we would say that that red circle is circumscribed about that polygon, right? And on the right-hand side, the circle is inscribed within. So if I told you on the left-hand side that the radius of this circle was 10, remember, you're always going to draw a radius that helps you. So here's a radius that helps me. So this guy's 10. Ah, here's another radius that helps me. This guy's also 10. Could you use this information and figure out what the area of that regular hexagon is? Yes, absolutely. Now let's look at the one on the right. Now it tells you that your radius is 10. So I'm going to draw a radius that helps me. Ah, so what role does the radius play here? So in this situation, my radius is my apothem, because look, here's my triangle, and I've already got my radius there. Cool? Because this guy right here, like one of my bases, is a tangent. And remember how we always talked about a radius is going to be perpendicular to a tangent at one point? So there it is. Cool? All right. So let's look at these last two problems, I think. Just last two. Yeah. So let's say I give you this guy. A regular hexagon is inscribed in a circle with a diameter of 30. So if the diameter is 30, that means my radius is 15. And so my setup would look something like this. And if you know it's a regular hexagon, you know you're dealing here with an equilateral triangle, which is kind of nice. It gets a little bit more complicated when it's not a hexagon, but don't worry too much about those. So a little trig is involved, whatever, but don't worry too much. And then you can find your area from here. And then last problem. So a regular hexagon now is circumscribed about a circle. So now I know my diameter is 18. So my radius is going to be 9. So here's my radius that's 9. And in this case, my radius is also going to be my apothem, which is kind of cool. I already know the perimeter of this hexagon. So it's just 1/2 my apothem times my perimeter. And you're done. All right, go tackle that worksheet, have fun, and I'll see you guys soon.